Section 13.4. The Wilcoxon rank sum test for two independent samples. This test is another one of our non-parametric tests that uses ranks of sample data from two independent populations to test whether or not independent samples come from populations with equal medians. So unlike our previous test, we are now gathering our data from two independent populations. And so the basic idea here is that if two samples are drawn from identical populations and the individual values are all ranked as one combined collection of values, then the high and low ranks should fall evenly between the two samples. And so if I have two samples, if I have sample 1 and then a bunch of sample 1 values, and I have sample 2 and a bunch of sample 2 values, then I'm going to take all of these values and I'm going to rank all of these values regardless of which sample they belong to. So I'm going to rank these essentially pretending like I don't know which sample they belong to. And if all of the high and the low ranks are pretty evenly dispersed throughout the two samples, then I can say that both of these samples have the same median. Let's say all of the high rankings are coming from sample 1 and all of the low rankings are coming from sample 2. Well, this is going to tell me that I probably have different medians in each of these samples. And so that's our basis here. And so let's go ahead and do an example. And as we go through this example, let's refer to our flowchart. Example 5. The table below lists course evaluation ratings for courses taught by female and male professors. Use a 0.05 significance level to test the claim that female and male professors have the same median course evaluation rating. And so looking at my null and my alternative hypothesis, I know that my null hypothesis is one of equality. I want to test the claim that female and male professors have the same median course evaluation rating. And so my null hypothesis can be that the median of these ratings are equal. So the median ratings are equal. And my alternative hypothesis can be that the median rankings are not equal. I'm sorry. The median ratings are not equal. Okay. And now let's refer to our flowchart for our next steps. And so in this test, I'm going to first find the z-test statistic using the following procedure. I know what the z-test statistic means. This is kind of using that normal distribution. So this is going to be a z-test statistic. And I'm finding this by first looking at the data as if the two samples are part of one big sample and recording each sample value with its rank. The lowest value is assigned a rank of 1, and in this case the signs do matter. So we're just ordering these from lowest to highest, regardless of which sample we're in. And so I'm looking at both of these samples here. And I'm starting with the lowest that's going to get a rank of 1. I'm looking for the lowest value in this data set. And I see that 2.9 is the lowest. And so this is going to get a rank of 1. And I'm just going to circle these ranks as I find them, because I remember that if I have any ties, then my rank is just going to be the mean of all of those ranks, of those values. And okay, so I have 2.9 as my first rank. Now let's find the next smallest value. I've got a 3.1. Is anything smaller than 3.1? No, and so 3.1 is going to be number 2. I'm looking for the next largest value. That's going to be a 3.3. I only see one 3.3, so that's going to be a 3. And next I've got 3.4, but I have 1, 2, 3, 4, 4 3.4s. That means that if I were to give them all a rank, it would be 4, 5, 6, and 7. But I don't want these to have different ranks. I want to find the mean of all of these ranks. And what's the mean of 4, 5, 6, and 7? Well, I know that that's halfway between 5 and 6, and so that's going to be 5.5. And so the rank of all of these 3.4s is just 5.5. So this is going to be 5.5. And I'm just going to circle this to show that it is my final rank. And it's very easy to make a mistake here, especially considering the fact that we do have a lot of decimal ranks. All right. And in the same way, I'm going to go through and rank all of these values. And I'd encourage you to maybe pause this video and do the same, and then we'll make sure we get the same result. And so now that I've ranked all of these values, I just want to double check something. The last rank should be the total number of values. So it should be the total sample size among the two different samples. And so if my last value is 27, I should have 27 samples. And let's just make sure we've got 12 from female. We have 15 from male. Okay, great. So we have a total of 27 samples. All right. Now that we have all of these values, let's look back at our graphic organizer and see how we actually calculate this test statistic. So now we want to find the sum of the ranks for one of the two samples. Now this is always going to be easier if it comes from the smaller sample, but it doesn't matter which. And so we're essentially going to declare one of these samples sample 1 and one of these samples sample 2. If I want to find the sum of the ranks for the smaller sample, I'm going to call my sample 1 that of the female professors. So to find this test statistic first, I'm going to find the sum of the female professors' ratings. And so this will become R, the sum of the female ratings, and my R is going to be equal, and I can do this in my calculator. And so now I'm just adding up these ranks. I'm not adding up the ratings, just the ranks. And I get 159.5, and so my R is 159.5, and let's just make this clear that it is the sum of the female ranks. And referring back to our organizer. Okay, now for the actual test statistic. N1 is the size of the sample from which the rank sum is found. Now we found this from sample 1, and so the size of the first sample, we actually calculated when we confirmed our ranking system here. And so the size of our first sample is going to be 12. And again, this is the female ranks. The size of the second sample is going to be 15, the size of the male ranks. All right. And now we need to just find the mean of ranks and the standard deviation of ranks using the following two formulas. And here I can see that it does in fact matter which I'm calling sample 1, because I see that this sample 1 sample size is multiplied by this numerator for the mean of ranks. And let's look at this test statistic. So I know what a test statistic does is it allows me, in this case a z-test statistic, it allows me to put this value on a normal distribution curve to see where it lies. Doesn't this look a whole lot like our formula for any regular z-test statistic, where we have the value minus the mean divided by standard deviation? So we're kind of doing the same thing here, but with ranks. And so let's first calculate the mean of ranks using this formula. And so the mean of ranks is going to be n1, which is 12, times n1 plus n2 plus 1 divided by 2. Well, this is just going to be 6 times 12 plus 15 plus 1. I know that 6 times 28 is 168. And so my mean of ranks is going to be 168. And next, I can calculate my standard deviation of ranks using this formula. And so this standard deviation of ranks will be equal to the square root of n1 times n2, so 12 times 15 times n1 plus n2 plus 1 all over n1. And calculating this, these 12s are going to cancel, and so this is going to be 15 times 28. But since this isn't actually my final answer, this is just an intermediate step, I really don't want to round. So I'm just going to find 15 times 28. 15 times 28 is 420. And since 420 is not a perfect square, I want to leave this as the square root of 420. All right, and finally, I can plug these values that I just found in to get my z-test statistic. And so my z-test statistic is going to be R, which is 159.5, minus my mean of ranks, so minus 168, divided by the square root of 420, so my standard deviation of ranks. And now this I can estimate because this is my z-score that I'm looking for. 159.5 minus 168 divided by root 420. And this is negative 0.415. Because this is a z-score, I'm just going to round this to 2 decimal places, so negative 0.41. Negative 0.41. All right, I've got my z-value. And now I need to find my p-value given this z-value. And so I can use the table or I can use my calculator. And since we used that z-table this time, let's use our calculator and we can go to second vars. I can then go to normal CDF. And with my lower bound of negative infinity and my upper bound of negative 0.41, and my mean of 0, standard deviation of 1, just to show that it's a normal distribution, I get 0.341. Now, be careful with this. I got an area to the left of that tail of 0.341, but what type of test is this? Well, because I'm just looking at equality here, I don't have greater than, I don't have less than, this is a two-tailed test. And since this is two-tailed, then I need to multiply my p-value times 2, and we said that this was 0.341. And I'm multiplying this by 2 to get 0.682. And so my p-value is 0.682. We can see that this is a very large p-value. We found the p-value from the standard normal distribution table or from our calculators. And then our grand conclusion is that if our p-value is less than or equal to alpha, we are going to reject the null hypothesis. If our p-value is greater than alpha, then we're going to fail to reject the null hypothesis. Same conclusion as always, really. Large p-value means we are failing to reject the null because p is not less than or equal to alpha. We are failing to reject the null. And let's see what this means in terms of our original problem. Well, we wanted to test the claim that the female and male professors have the same median course evaluation rating. And so our claim was the null hypothesis. And if we're failing to reject the null, then that means that there's not sufficient evidence to reject the claim that the male and female professors have the same median course evaluation rating. And so it's looking like the ratings are really not dependent on gender.